Mohamad. I'm happy, as you show on my face, I have a friend. Actually, you visited me in Montreal 10 years ago.
Yeah.
10 years ago. So, and then 10 years after in China. So, next 10 years, I'm not sure where we'll be. So, Professor Machado, he's actually got his master and PhD and EE from the Federal University of Santa Catarina, which I spent 3 months sabbatical at that time. Again, more than 10 years, I don't know. And then he was focusing on many things related to analog to talk about, but he got some specialization, I think visiting scholar or visiting student in student-centered learning in Finland at Tampere University. Okay, and next he was visiting a PhD student in Polytechnique in my group in Montreal for 1 year at that time. He was working on energy harvesting and for application like medical devices, as you know about. He was awarded the 2015 Best Brazilian PhD thesis in microelectronics. The topic was advancement of extremely low voltage electronics. Okay, after that he has been with the Brazilian Federal Institutions Network of Science and Technology. Presently he is a full professor at the Federal Institute of Sao Paulo, the largest federal education institution in Brazil. Okay, Professor Machado has worked as the advisor of many students in different projects related to ultra-low voltage electronics, energy harvesting, and assistive technology, and of course for biomedical circuit and system. In recently, 2022, he co-authored the book Ultra-Low Voltage Circuit Technique for Energy Harvesting, published by Springer, you can find online. So without delay, the floor is for you.
Okay. Thank you, Professor. Can you hear me? Yeah? That's okay? Okay. Thank you for the nice presentation. I will talk about the challenges and opportunities for ultra-low voltage energy harvesting designs.
Up and down.
Yeah, okay, yeah, another direction, yeah. So I will talk about a little about the Federal Institution of Education, Science and Technology of Sao Paulo, Brazil. That's the largest federal institution of education in Brazil, with more than 40 units and more than 50,000 students in the state of Sao Paulo. Brazil is a large country as China. Yeah. And we have here in that part, that's the state of Sao Paulo. Okay? The main question of this study is one, how do we significantly decrease the voltage limit of the special blocks? Actually, the converters, oscillators, and rectifiers. Okay? And number two, how do we improve these circuits about integration, efficiency, minimum voltage, and modeling? I will try to address these two main topics inside the presentation. Most of this, the content that I will present today will be inside this book. That's Ultra-Low Voltage Circuit Techniques for Energy Harvesting, cooperation between the Federal Institute of São Paulo, from me, Federal University of Santa Catarina in Brazil, and Professor Sawan from here, Westlake. Oh, okay. No, okay. Sorry for that. Okay. presentation is divided in 5 parts. The introduction, I will talk about the area of energy harvesting and ultra-low voltage also. I will talk about two special blocks that we use in an energy harvest. That is the oscillator and the rectifiers. After some implementation, we use both blocks, and at the end I will present very briefly high efficient designs and the summary of this presentation. Okay? So, introduction. The main motivation of this work is energy autonomy. So, sensor network related to the agricultural, monitoring, entertainment, or quality of life, and biomedical applications, especially implantable, as you know a lot of this topic actually, requiring power, yeah? Some attractive sources that can be used to generate this power autonomy or the thermoelectric generator, that is a body environment, like here is my arm actually. You can generate voltage as extremely low, like 500 millivolts. Photovoltaic cells used in a dark room, for example. You can use this kind of energy even you have very or extremely low voltage. Glucose fuel cells, that I know that some person here are working in this subject, and you can generate voltage in a implantable way too, but the voltage could be very low, especially if you get this energy along the time, yeah? The voltage could decrease with the time. Energy by trees could be gathered, for example, a difference of pH between the tree and the soil can generate voltage very low too. And of course, new materials like graphene are being used to generate voltage in a different way. In this case, for example, is a generator that is based on the air unit that can generate voltage as low as 15 volts too. Okay, and now we have a hot topic actually. It's how to generate energy from the RF signals. So we can see in recent papers that the energy can be generated from signals very, very low. The power is around minus 20 dBm. That represents 22 millivolts to considering a 50 ohms antenna. So the main question that we have is how can we boost the ultra-low voltage levels to power supply the electronic circuits nowadays that require at least 500 millivolts in general, yes? And how can we do it in an efficient way? I think that's the main problem nowadays, yeah? So, about some history, in 1978, a group from the company, Bulova, proposed a circuit that could, wristwatch actually, that could get energy from the, using a thermoelectric generator from the temperature, the body temperature. More recently, another group from 2010 from Washington University proposed a circuit that could start up from 20 volts. I think this was like a breakthrough. But in that moment, the circuit required a startup gadget using a pre-charger, capacitor, or a battery. Another group, one year later, from MIT, proposed a circuit that could start up from 35 millivolts. But in that moment, it uses a mechanical switch to start up the circuit. A little bit after, in 2012, another group from Tokyo University presented a paper that started up from 80 millivolts, but it requires a post-fabrication in an oscillator that is a little bit complicated in that moment. Okay, more recently, we had a publication from Federal Santa Catarina, Brazil, and in cooperation with Polytechnic Montreal, that the circuit operating from 7.5 millivolts and start up from 11 millivolts. Okay, and more recently, in 2000, last year actually, we have a paper from the University of Hangzhou, not Westlake, but in Hangzhou, sorry, And the people could working with 5 millivolts in 90% of peak efficiency. Okay, that's the maybe around the state of the art nowadays. So the question that we have now is how to deal with the ultra low voltage to start up from 10 or 20 millivolts. The integration, so because this the most part of the topology that we have presented requires an external component like inductor, a good inductor actually, and you have to deal with also with efficiency. It's not easy to comply with 3 axes actually. So the classical topology that we have now, that's normal to see, we have 2 converters, a cold starter converter that can work with similar low voltage, a second converter that work with much higher efficiency, yeah. And this topology has some constraints that it has high complexity. It's not easy to deal with the 2 converters that are very different. They require elevated area, and I think that the main part that's not good is not fully integrated. In general, the second converter requires an external inductor, for example. Right? So before I go to the circuits, it's nice to talk about the modeling. So in these studies, we have used model of the transistor based on the surface potential. That is called the advanced compact MOSFET from the group of Brazil, of Westlake, Brazil. And we can split the current in 2 parcels, a forward and a reverse, and you can say this in terms of the normalizer. And using this model, we can represent the voltage levels, source and drain, in relation to the currents of the transistor. It's a continuous expression that is valid to all regions of operation of the transistor. This is important too because you work with very little voltage, and sometimes, of course, you go to the subthreshold, to the linear area of the transistor. So now we can represent the transistor in terms of the transconductance, the GNS, GND, and we can have an expression to the voltage, to drain source voltage directly from the transconductance or in terms of the current. So it's very useful equation that we can use to model the circuits, for example. And now this expression, you can see also the strong conversion operation in another parcel that is referring to the weak inversion. So this could be very good to model. Okay. A little bit about the diode. So in this studies, we're considering the shocking equation, that's the exponential law of the diode, okay? And in general, this connection could be very useful when you have the DTMOS actually. You have the connection with the drain, hook, and at the same time the gate of the transistor. If you get this picture, we can see that you have 2 diodes in parallel way, and this first diode is the junction diode that is the same direction to the MOS diode that is the main diode of the circuit. So using this connection, we can represent the current of the transistor like a diode. So if dVt is a constant, we have this term that is equal to the saturation current, so we can model the circuit like a diode, for example. So one more thing that is good to think about is how to choose a transistor that works with these ultra low voltage levels. So in general, I think that nowadays is very common to use a zero VT technology or native transistor technology. And here we have a comparison between 3 types of transistors, zero VT, low VT, and standard. And you can see for voltage below 300 millivolts in that area, the zero VT transistor has much higher FT, the parameter of the transistor, the FT, the frequency of the transition of the transistor, is much higher than the low VT or or standard transistor. Yeah. For the other side, you have a comparison between a diode connection of the 0VT transistor in blue one, and this is the standard transistor in gray one. So we can see that the saturation current of the 0VT transistor is much, much higher, around 500 times the saturation current of the standard transistor. So this characteristic shows that the 0VT transistor has a very good capability to be used in ultra-low voltage circuits. Okay. So now I will talk about the one specific block that's important in image harvest circuit, that is oscillator. So in a DC-DC transfer, DC-DC conversion, the oscillator in general is the first block that can work with extremely low voltage from the image harvest sources. So it must operate from extremely low voltage with enhanced swing amplitude and with capability to be integrated or fully integrated actually. Yeah. So about the history of this block. So in 1994, a group from Stanford University proposed a circuit that could start up from 100 millivolts in a fully integrated way, but in that moment, this process was not commercial, and they was doing some tests actually at that moment, yeah? Changing the VT of the transistors. Another publication, but not a study publicated in a magazine, was showed that the circuit could start up from 5.5 millivolts using a big transformers, like very, very big actually, and this result was available online, was not publicated. Another work from my work actually proposed a circuit that could start up from 3.3 millivolts in that time, yeah, using external inductors. So I will talk about how to get a reduction, for example, some insights. Yeah? Okay. If you get a normal ring oscillator, like a CMOS ring oscillator, how to decrease the minimal voltage that it's operating? One way to do it is replacing the PMOS load, the PMOS transistor of the oscillator, to an inductor. If you do it and use a transistor that operates with very low voltage, as a 0VT or native transistor, it can oscillate with very supply voltage, and another good characteristic is that it can generate at least 2 complementary phases or more if you need. So how to model it? Yeah? So we can get one single stage, and we get some transfer function of that. So with that function, we can see the oscillation frequency and see also the minimal transistor gain to start up the circuit, to oscillate, to start up the oscillation of the circuit. So if you have now, if you get the transistor model that I told before and the equations of this circuit, we can express the minimal voltage to start up oscillations given by this expression, okay? And we have parcel that refers to strong inversion, and we have another parcel that refers to weak inversion. Yeah? So now, if you get only the weak inversion parcel and disregarding the inductor losses, we have the minimal limit of the topology. That's around 18 millivolts. If we compare with the Mendel limit, that's a limit of the CMOS inverter, we have the half part of this limit of the digital inverter. Yeah? So it's a good reduction, and we can go below the CMOS inverter. We have 2 implementations, one using 7 stages, operating from 63 millivolts, and another using 2 stages that operating from 46 millivolts. That time was really good result, but now we have more advancement. Okay, how we can decrease this voltage limit, yeah, and how to increase the voltage swing that's important too. Yeah. So one way is to having some boost inside the stage. So you can use a second inductor to do it, or use an enhanced swing topology, yeah? Like Colpitts, enhanced swing Colpitts, I will talk about in the future. So now, if you have the voltage boost here inside the stage, you can reduce the minimum voltage to this expression, and if you have the second inductor much higher than the first one, we have no higher voltage limit of this topology. So it can work with extremely low voltage. Okay. Here we have some implementations. So using off-the-shelf components and zero-unity transistor, we can start up from 3.3 millivolts. So it works with very low voltage. And this cushion, the peak-to-peak amplitude could be much higher. In this case, it's around 100 millivolts. So, okay. Here we have a fully integrated. Okay, but okay. We have a fully integrated version of the circuit with 4 inductors, and it starts
You can use your finger, for now.
Yeah, I think it puts more energy. Yeah, and this circuit could start up from 30 millivolts, and the results are very close to the simulated one. That's 29, so it's a good result actually at that time. Now we have another way to do it. Here we have a normal Colpitts oscillator, and we can change it. We can replace the current of the polarization by a second inductor, and using that, the limit of the topology is given by this expression. And if you have the capacitor 1 much higher than capacitor 2, there is no hard limit to. So it can work with extremely low voltage, according, of course, the inductor losses. Yeah? So here we have some experimentations using off-the-shelf devices. It can start up from 15 millivolts using a fully integrated way. We can process that, yes. We can start up with 86 millivolts. Okay. Another way to do it is using transformer. Okay, and here, if you use a transformer, you have an AC gain in the feedback, in the loop, yeah? And with this, we can enhance the swing amplitude of the circuit, and the circuit could be used in the startup and also in the main converter, okay? That is used a lot, actually. So here, we can see this transformer used in the commercial converter, and some other publications using this kind of topology, including a fully integrated way to design some transformers too. Okay, the LC oscillators we have good results, but the area could be a constraint, of course. Yeah. So another way to think about the ultra-low voltage oscillators is using a CMOS. Not using an LC external, for example, in the previous one. So using a CMOS oscillator, we have it's not necessary to use any passives. The area is reduced, but the voltage is cushioned. The peak amplitude could be much lower. It's not good characteristics of them. So here we have the limit of the topology that I told before. That was around 36 millivolts. That's the main fundamental limit of the inverter, actually. Okay. So some groups have studied the Schmitt trigger as a basic stage of the oscillator, and we have you can approximate the minimum voltage of around 31 millivolts. That's below the limit, and this work presented a circuit operated from 53 millivolts, okay, of the startup. And another group proposed this circuit, use it for power too. That using a stick inverter, more inverters here, and with this topology, we can reduce the leakage current and increase the voltage gain. So this circuit was tested and it was able to oscillate from 57 millivolts. Okay. Nowadays, I think that's a very recent publication from people from Polytechnique Montreal. The people can oscillate in a circuit with 32 millivolts. It's very, very low actually, using an SOI process in a modified change trigger using more or less the both circuits that I presented before. Yeah, this circuit could be very useful. I think that's the main problem of this is the exclusion that could be very very small. Yeah, but I think that's a good result that they have. Here we have a comparison with some fully integrated and using external components, and you can see that the best result that we have is using more inductors in the both fully integrated and using external components. Yeah. So I think that's an opportunity to research is that about this topology. There is no studies about the power conversion efficiency of this topology. Even that this is used a lot in the energy harvest field, there is no studies about the efficiency. So this could be a way to improve actually, yeah, and to use this as the power, the main converter actually. It's not employed also as the main converter. So this topology is used in, I think that's in 90% of these studies that we have now. It's used as a first converter. It's only to start up the circuit. It's not. People don't care about the circuit after some time and some startup. Yeah. So this could be an opportunity to improve this circuit and avoid to use a more complicated second converter. Okay, now I'll talk a little about the rectifiers. Rectifiers are important block too, because they are used in many kind of circuits, not only to energy harvest, of course. So, in general, this kind of the circuit or this application requires that it must operate from extremely low voltage, can be used together with ultra-low voltage oscillators, with capability to be fully integrated too. Yeah. Also, this kind of circuit is very much used in RF energy harvest. Yes, because of course it can be used in a lot of kind of topologies. Yeah. The problem that we have that in general, this topology has the efficiency is not too high as a switch topology, like an inductor topology converter. So the main question that we have to do to thinking about when we design this kind of rectifiers is how to estimate the diode forward drop voltage. So if I can estimate the voltage over the diode, I can estimate easily the output voltage. Yeah? But how to estimate that? If you considering you are considering the voltage over the diode like 0.7 or 0.6, that is normally used in the electronic books today, until today, yeah, it's quite hard to use for this application that you have voltage as low as 100 millivolts or even less, 10 millivolts, for example. Yeah, so we cannot consider that approximation. Yeah, so in fact, V1, the voltage over the diode, depends on the temperature, the voltage, amplitude, the peak amplitude of the signal, the load current the current that you pass through the diode, and the characteristics of the diode, like the saturation current. Yeah. So how to model it? If you get, if you can, if you want to have an expression to the V out, you have to consider the circuit operating in steady state. So don't care about very much the beginning of the circuit. You can consider the ripple is very small, so the capacitors are very large. the diode is modeled by the exponential model that I told you before, yeah? And the average current in the diode, the average current that passed through the diode, is equal to the load current. If you consider that, you can solve this equation and you can calculate the voltage over the diode, okay? And here, ID, you can consider this expression, and VD, the voltage over the diode, considering the voltage, AC voltage at the input, okay? You can get this expression. So, if you have the voltage over the diode, you can easily find also the voltage at the output of the circuit, okay? And one result is this expression. So now we can see in that picture that the output voltage is dependent, it's very much dependent on the load current over the saturation current of the diode. So this ratio is very useful, and you can use this to design a good rectifiers actually. Yeah, we can see also that the output voltage, that is normal thinking, yeah, is dependent on the peak amplitude of the AC signal. Yeah, but it's dependent also from the load current that you have. So another topology that is very much used in ultra-low voltage is the Dixon charge pump. And this topology is very useful to ultra-low voltage and use two complementary AC signals, V1 and V2. Okay, it's a little bit, you need to have two complementary signals, and you can use DC reference in the output and in the input, and the output is added by this value. Okay, you can add this value here at the output. You can see. So this circuit, there is one characteristic that the first diode and the lastmost diode has the waveform different than the rest of the diodes. So these characteristics you have to take in account, because the voltage, the drop voltage over this and this transistor are different from the rest. So considering that we can have the same, can follow the same procedure, and we have the output voltage expression to this topology in terms of the same parameters than before. We can express to the power converter efficiency and the input resistance of this topology too. Okay, that's so useful. Here we have output voltage in terms of the load current over the saturation current, and you can see that the same behavior than for the rectifier. Yeah? Okay, and now we have these expressions too also, as I said before, for the power conversion efficiency, so the PCE, and you can see that the power conversion efficiency is much more, impacted, is much dependent. Oh, okay, no, it's not okay. I'm trying the second one here. Yes, you can see that the efficiency depends on the load current over the saturation current. So if you have a load current, specification of the load, you can design a good rectifier considering or design exact value that you need of the saturation current of the diode. Okay, so you can maximize the efficiency. Also, you can see that the power conversion efficiency is strongly dependent on the peak amplitude. Okay, so it's good to see about that. In general, for example, in an RF design, you can maximize the amplitude of the signal, and so we can put the circuit operating in a more efficient way. And so, because that we can try to improve the peak amplitude a lot in the initial field. So now we have another important circuit, that's a voltage multiplier. That's the circuit that we can describe in the basics of electronics. Yeah. If you get any stage voltage multiplier like that, you can see that it's very similar to the Dixon charge plug that's presented before. So we can see that we have one, in this circuit we have only one AC source, and now for the Dixon we have two sources. If you get the second source, if you don't care about the second source and grounded it, the circuit could be very similar, okay? And you can model the circuit in the same way. Okay, now we have expressions to model in the same way for the full wave voltage rectifier also, okay? And the same consideration that I told before, we can have to this circuit too. Okay, in the book that I told you in the beginning, you have a summary of the expressions considering the V out, the efficiency, the input resistance, in terms of the square and sine wave, okay? And so if you using these equations, you can find inside that book. Oh, so I think that's, now we can answer some questions, yeah? So how do we improve the rectifier? How to improve especially the efficiency and get the voltage, for example, and the efficiency that you need, yeah? So one way is using a proper diode. So here we have some useful diodes that people are using actually in RF or in DC-DC conversion, okay? But sometimes, of course, you don't have the size to use a discrete transistor diode, so you have to go to the integrated. And how to choose a right transistor to design a ultra low voltage design. So using a 0 VT or low VT could be very useful, and maybe we can, if you decrease the VT of the transistor, it means that you can increase the saturation current. So to get the right IS parameter, maybe you have to deal with the 0 VT transistor or at least the low VT transistor, okay? Another way to decrease the voltage of the 0 VT, to decrease the VT of the transistor, it's using a book polarization technique that at the end is the same thing, yeah? You can polarize the book and you can decrease the equivalent threshold voltage of the transistor. One way to do it is using a DT-MOS connection that I told you in the beginning, okay, that you polarize the book too. Another way to do this polarization is using cross-couple connection that people has used a lot, the polarization of the book too. Okay, in this connection, we replace the diode connection by a switch. Yeah, so this is based on the Dixon topology. We have two complementary sources employed in many ultra low voltage energy harness studies, and if you get the modeling, this paper has some insights about the modeling of this specific circuit, okay? So another way to improve the rectifier efficiency is using active diodes like that, but to that, there is no much studies about the efficiency applied to ultra low voltage, yes, but I think that could be a good try, because this circuit could working with efficiency of order than 90%. That's very high, but I think that the studies are not too low. Why? Why? It requires a polarization of the amplifier, so it's quite hard to get this polarization to ultra low voltage, yeah? But if you can improve a lot the efficiency of this kind of circuit. So another way to improve the efficiency is to use to boost the amplitude of your signal. Yeah, so if you go to a higher amplitude, you can go to a higher level of efficiency. Okay. So I will talk about very little about the implementations that you have done. So we have three implementations, one fully integrated using some components externals. No. So here we have full integration, full integrated way. Yeah, and this circuit could start up from 73 millivolts. Yeah, so we have the oscillator together with the charge pump. Now we have another implementation using only the external inductors, and you can reduce the minimum voltage to around 16 millivolts. And this circuit is wire bounded to the PCB to decrease the losses to show the result. And now we have one implementation using off-the-shelf devices, actually off-the-shelf diodes and inductors, and it can start up from around 4 millivolts. Okay. Now we have co-design, and you try to figure out which circuit could be more efficient and better, the voltage multiplier or Dixon charge pump. And in this co-design, this methodology, we can see this axis means that the number of the stage that you need to use in order to get the specification, and from the Dixon will be much lower than the voltage multiplier. So in general, Dixon charge pump has a working with in a better way with higher efficiency than the voltage multiplier. So now I will present some high efficient design that we have. So in general, as I told before, we use converters, one like a rectifier, that's easy, start up at extremely low voltage with capability to be fully integrated, but work with low efficiency at ultra low voltage. On another side, we have inductive boost that work with high efficiency even at ultra low voltage, but need external inductors and a capacitor, and is not able to self-start at ultra low voltages. So using the both words like that, as I told before, yeah, to have an implementation, and I will show the results. Okay. Here, this circuit, how it works. Actually, we have three phases. Phase A, you have the cold starter, only the rectifier is working, and the oscillator plus rectifier is working. And the second phase, the two converters are working. And the phase 3, only the main converter, the main efficiency converter is working, and it's a steady-state operation that can work with high efficiency. If the low voltage could be below the limit, the circuit go back to the first phase and start up again. There is an implementation of the circuit that is in our book that start up from 11 millivolts and operating from the minimum voltage of 7 millivolts. That's the difference between cold start and operation. And the maximum efficiency is around 85%. Okay, it's results from it's in our book from the Rafael Radin, actually. He works in that project. Now, summary this presentation, we can recognize some challenges in this field. So I think that's the main thing that we have to care about is considering the three axes of the design. Okay, so implemented the ultra low voltage harvesting circuit in a fully integrated way. So it's not easy to do it in a fully integrated way. So it's some challenge yet. Yeah, I think that's some trends we have. The use of SOI technology to obtain low levels of VT. That's possible to use a lot of. You have to choose. You can choose actually the VT. The book polarization. You can polarize the transistor, and you have low leakage current too. Yeah. So three characteristics that are very good in this field. Okay, to ultra low voltage. And another thing that we can thinking about to design. If you maybe want a good application, for example, or would try to do a good result, a strong result, is elevate the frequency to work with a fully integrated inductor instead of using an external good inductor, yes, but if you go inside you have to go to the higher frequency, could be another challenge, but I think there is some room to explore this topology. So the opportunities about you have in this field, energy harvest has continuously been a hot topic in circuits and systems. I think that's some people are working on that in that moment, yeah. Improve the converter efficiency at ultra high voltage. Maybe if you're thinking about using only one converter instead of two, could be an opportunity too. And you have 6G cellular networking coming with many opportunities and challenges, and then energy harvest. Yes, you know that 6G has a high frequency and high necessity of using energy harvest field too, yeah, because you have a lot of points to connecting and send information, and at this point require energy. Yeah? So energy harvest, I think that is on. I think it's the end. That's the exact time. Yeah. I forgot to use the power supply. Yeah.
Oh.
But this is last slide. The other is by day.
So means how you calculate this?
Yeah, it's perfect time. Yeah.